So good afternoon. We are ready to start with some delay. So let's see if we can recover during the 5 presentations. So we have a long schedule. It's going to be a long but pleasant afternoon. For those of you that were not here this morning, I would just like to say a few words. This is the 8th International Nigel Priestley Seminar. It's the 22nd seminar this year in 2024. So it's a long tradition. There's a long history behind these seminars. From a few years until now, we have started to foresee the doctoral exams during the seminar. So this is the reason why we start with 5 candidates that have spent more than 4 years, more than the last of the 4 years of their lives working for this day, let's say. So it's a special day for them, a special day for the families and the friends. So let's enjoy the afternoon with them. And we have candidates coming from many different parts of the world. And we have also a committee, an evaluation committee coming from different countries. We have Professor De Luca from, she's Italian, but she's from the UK professionally. We have Professor Vlatko Sesov from North Macedonia. And we have Professor Romão from Portugal, Porto. So thank you very much to the 3 of them also for accepting this, this task. Let's start so that we don't further delay our program. Karim Al-Jawari from Palestine will be the first candidate presenting his thesis in the field of holistic seismic rehabilitation. I will let you read the full title. Thank you, Karim. Go ahead.
That was sweet. Thank you. So, good afternoon, everyone. Thank you all for being here. It really takes a lot of nerves to be able to stand in this position. However, I'm trying to look at this as more of a celebration rather than examination, because it's going to be an opportunity to present my 4 years of work about integrating sustainability, direct and indirect losses towards optimizing and designing seismic retrofitting. This work was done in collaboration with Professor Carmine Galasso and Dr. Roberto Gentile, to whom I will be always deeply grateful. I don't have much time to discuss all details. That's why I'll try to focus on the novelties and the conclusions. And I hope you enjoy this presentation, and let's get started. I'd like to begin by the reasons that motivated my research. So, we all acknowledge that structural retrofitting is a very cost-effective tool to enhance the seismic performance. The problem is that traditional decision-making frameworks for retrofitting rely typically on the seismic damage and the corresponding direct losses, or let's call them repair costs. However, there are other crucial metrics like sustainability and indirect losses due to downtime that are typically overlooked in the process, and that's because of the lack of suitable models to characterize them. Another issue is that retrofitting designs are typically not optimized based on performance targets or risk targets. And again, this is due to the fact that this process might be heavy in terms of computational effort. So, I divided my presentation into 4 different parts accordingly, in which each part tackles a particular challenge from what I mentioned before. Part 1 is about a practice-oriented approach for the design of seismic retrofitting. And I remind you here that retrofitting design and optimization could be heavy in terms of iterations. And this becomes even more complex when we look at building portfolios, because if simply I don't optimize, it means I don't have full control over the reduction in fragility and seismic risk. So the question that comes to my mind here: can I improve the retrofitting design process in a way that allows me to control the desired level of fragility without significant iterations? That's what we'll find out. This work basically depends on investigating the relationship between 2 parameters. The first one is the ratio between displacement capacity and life safety demand. And for ease, let's call it capacity demand ratio. This can be simply evaluated by using pushover analysis combined with the capacity spectrum method. And it's a very simple performance metric that gives you an idea on how the seismic performance is evolving. The second parameter here is the median values of fragility relationships for different damage states. And the fragility here are basically the conditional probability of exceeding different damage states given the ground shaking intensity level. We are looking here at 3 different damage states, which are moderate, extensive, and near collapse. And in normal cases, I might require to do nonlinear time history analysis to derive these relationships. I'm looking here at a 5-story pre-code frame that represents Italian buildings before the 1970s, which is designed for gravity loads only. This was modeled using OpenSea's accounting for different failure modes, and I've run an initial assessment for that building. On the left side, you see the pushover curves together with some damage observations, and on the right side, you can see an illustration of the capacity spectrum method. But the most important part here is that the capacity-demand ratio is equal to 42%, which means that my building has less than half of the required capacity. And therefore, I enhanced its performance by considering 3 widespread strategies. The first one is wrapping the columns with FRP, we have steel jacketings or encasements, and finally we have the traditional reinforced concrete jacketing. After that, for each strategy, I designed multiple retrofitting layouts that could vary in terms of detailing, geometry, and number of retrofitted elements in a way that achieves an incremental improvement in the seismic performance. And I ended up having between 13 to 18 cases for each strategy. Then I derived the fragility relationships for both the as-built and the retrofitted cases. And we can see here that the fragility curves are shifting towards the right, meaning that the structures are becoming less fragile. So let's now look at the relationship between the capacity-demand ratio and the median fragility. And we can see here from a visual perspective that it's almost linear. This is something I also verified in terms of goodness of fit by fitting the lines that you can see in the slides, and on the table we can also observe the exact formulas. I also verified that in terms of structural mechanics just to make sure that it works. So now that we know that the relationship could be almost linear, it means that I don't really need 15 or 20 points in order to fit the lines. 2 or 3 points are going to be enough. And given that one of the points is going to be the as-built structure, then the other 2 points could be any retrofitting layouts that achieve a better performance compared to the as-built structure. So, how do we use this approach? We start by selecting the desired level of median fragility. Let's say it's for damage state 2, and then we get estimated values for damage state 3 and 1, and finally we acquire the target capacity demand we have to achieve during the retrofitting design process to guarantee the desired reduction in terms of fragility. So, key takeaways part 1. We have a linear relationship between capacity demand ratio and median fragility. This can be used in 2 ways. Way number 1, we start with the median fragility, we get the target capacity demand ratio, or the other way, I might have a random retrofitting layout, I know the capacity demand ratio, and I just want to estimate the median fragility without conducting extra analysis. Let's now move from fragility into seismic consequences. And here I'm presenting a simulation-based approach for deriving consequence models of repair time and repair cost. We are all familiar with this framework, which evaluates risk by integrating 4 different parameters, which are the seismic hazard, the response analysis, the damage evaluation, and the loss assessment. And there are 2 main ways to apply this approach. The first one is the component-based FEMA P58 analysis, in which the losses in a building are evaluated by aggregating the losses in individual building components. And of course, in that case, I'm going to have to define a full inventory with all the components and their fragility and vulnerability data, which is not very straightforward. That's why I prefer to use this approach for individual buildings. On the other hand, losses can be quantified at the building level based on the global damage state sustained by a building. And to do that, I'm going to have to combine fragility relationships with the so-called global consequence models. These are also well known as damage to loss ratios, which are basically the loss corresponding to a particular damage state divided by the replacement cost. This method is easier to use, it has less input. That's why I prefer to use it when I consider building portfolios. And since I'm interested in portfolios, I'm always pretty skeptical about the selection of these consequence models because they can bring a great deal of uncertainty. And many of the available models in the literature could be generic, deterministic, or maybe based on a limited set of data. So the question here, can I use modeling and simulation in order to come up with a more refined models for these damage to loss ratios? That's what we'll see. I decided at this stage to expand the range of case study buildings so that I make the work more useful for the future. And we have 9 reinforced concrete frames with 3 different height categories, 3 and 5 and 8 stories. And they have also 3 different design code levels, which are the pre-code frames, low code, and high code frames. I followed exactly the same modeling strategy using OpenSeas, and then I identified 4 different global damage states. The first is slight, moderate, extensive, and near collapse. After that, I run pushover analysis in order to capture or map the damage states in terms of maximum interstory drift ratio, as you can see in the following figures. Step number 3 would be analyzing the nonlinear response using the multiple stripe approach. This is a sample of the results, and eventually using the output in order to derive the fragility relationships. Step number 4 would be conducting the risk analysis using the component-based FEMA P58 approach. And here I defined a component inventory that is suitable for Italian components. And I identified fragility and consequence models for these components, but I made sure that all these are selected from Italian references because I wanted the results to be representative and meaningful. In this figure, we can see the realizations of loss given the ground shaking intensity. So what we're going to do now is a conditioning process in which each one of these realizations is going to be connected with the global damage state. And to do that, we simply have to compare between the maximum interstory drift simulated, which is the demand, and the interstory drift for the damage state occurrence. And accordingly, we can separate these realizations and beta distributions to represent the consequence models. So the first output is the damage to loss ratios for 9 different frames and 4 different damage states. They are represented visually and also in terms of tables. We do have mean values and coefficient of variation. The same was done for the damage to repair time ratios. In this figure, we see an interesting comparison between the damage to loss ratios that I acquired and the one that I could find in HAZOS, which is one of the widespread references for global risk assessment. And I found significant differences that could be 15%, but maybe up to 140%. And that's why the selection process for these models is quite crucial for accuracy. So, key takeaways part 2. We have now a simulation-based approach to develop consequence models. I did it for loss and for repair time, but it's actually valid for any type of consequences. And finally, I found significant difference I found in my work. Moving now to a different type of consequences, which is the earthquake-induced environmental impacts or sustainability. Now, the question is, why sustainability is important? That's because 36% of greenhouse gas emissions are produced by the construction industry, and they lead to impacts like the global warming and the climate change. This situation becomes even more critical in earthquake-prone regions. That's because buildings are going to experience damage, and this means that material production, more filling, and this means more carbon emissions. The problem is that we don't have sufficient models for Italian buildings that quantify these carbon emissions either at the component level or the building level. So the target here is to derive these models and to use them for risk assessment. So I have the same component inventory here. I didn't change it, but I defined different damage states or that describe the increasing levels of damage conditions for the building components rather than the building as a whole. And after that, I defined suitable construction activities or repair activities that could include demolition, construction, maybe finishing and disposal. But the most important part is to identify the material quantities corresponding to these actions. And of course, I considered also the geometric variability using Monte Carlo simulation. Step number 3 would be evaluating the carbon emissions from the repair activities. And I did that by developing a database that contains carbon factors. These carbon factors identify the carbon footprint per material unit quantity. And to do that, I refer to an Italian platform that has environmental impact data from more than 60 Italian manufacturers and more than 230 product classes. So once I have this database, I just multiply it with the material quantities, and finally, I get the embodied carbon of repair activities. So naturally, step number 4 would be aggregating the carbon resulting from different repair activities per each damage state, and I ended up having these consequence models for building components expressed in terms of median and dispersion for different damage states. Now we have all the inputs needed to conduct risk assessment, and I here have the same 9 RC frames I talked about before, and I'm using the same FEMA P58 risk assessment approach. The process is exactly the same. The only difference is that in terms of using consequence models for euros, for money, I'm using consequence models for carbon emissions. The first output in the process is the environmental loss curve, which expresses the mean annual frequency of exceeding different values of embodied carbon. Now, once we integrate this curve, we get a single parameter called the expected annual embodied carbon, which gives us an indicator of the carbon emissions from seismic damage on a yearly basis. Doing this integration for all the 9 case study frames, we get this nice colorful matrix expressed in terms of number of stories and design code level. Of course, whenever we have higher stories or lower design code level, the expected annual carbon is going to increase. But in order to deepen our understanding for these values, I'd like to make some meaningful comparisons. The first one, let's see how the embodied carbon of seismic damage comes as a fraction of the embodied carbon for initial construction. This fraction is equal to 15% in case of the high code frames. It increases to 22% in the low code frames and become as high as 30%, almost 30% in the case of pre-code frames. I've done another interesting with the car story frame into account. We found that the carbon emissions of seismic damage are equal to the exhaust emissions of 10 cars during their entire service life, and they are equal to the embodied carbon of producing 81 cars, which is a significant number. After that, I applied the same simulation-based approach to get the consequence models at the building level, and I ended up having damage to embodied carbon ratios exactly like I had before, damage to loss ratios. During this part of the work, there was a question in my mind, which is, are repair costs and embodied carbon correlated? And to answer this question, I plotted the repair cost realizations on the x-axis versus the embodied carbon realizations on the y-axis. That the relationship is the same can be observed when I plot loss ratio versus it becomes a bit trickier because we saw before